This is part 3 of structure and cross-linguistic phonetic realization. So in this part of the talk, we're going to be moving away from stop VOT and turning instead to sibilant place of articulation. And we'll be first looking at variation across talkers, once again in American English, and then eventually getting to some cross-linguistic extensions. So at this point, uniformity and structure variation could just be about stop VOT. Alternatively, it could be that everything's correlated. The speech sounds are coming from the same vocal tract, and so maybe that's the underlying source of the covariation. Does it really have to do with a shared distinctive feature? So in this section, we're going to apply the predictions of this uniformity constraint to the phonetic realization of sibilant place of articulation. In American English, we have the sibilant sa, za, sha, ja that we'll be working with. First, we're just going to focus on the phonetic realization process for sa as an example. So on the left-hand side, we have the phonological surface segment with some relevant distinctive features that might be part of the bundle here. So we have plus anterior, which indicates the place of articulation, minus voice, which indicates the voicing status. These are then mapped to more precise phonetic targets that, again, here we're specifying them articulatorily, though they could be perceptual motor, they could be auditorily specified. We think in this case it makes sense to use articulatory targets, but open for debate. So in this case, a natural phonetic target abstract for the anterior feature might be something like constriction location. So where exactly should the tongue go? What's the coordinates in the mouth where the constriction should be made? Other phonetic targets that might be relevant just in the articulation of an S would be the constriction width, the state of the glottis, but we're going to focus on the phonetic targets for the for the anterior feature in general. These phonetic targets, of course, are then articulated physically and give rise to an acoustic physical form. So as I said before, American English has the segments sa, za, sha, and ja, and they have the following feature. We'll assume they have something like the following feature matrices. The key thing is that S and za share a place of articulation feature, which we'll call plus anterior, and sha and ja share the contrasting value, the minus anterior feature. And the phonetic target, again, will be the constriction location. As I said before, we're focusing, though, on acoustics, not articulation. So we need to identify an acoustic measure of the constriction location. A good candidate for this is the mid-frequency spectral peak. What is the mid-frequency spectral peak? This is actually not a common measurement, even in phonetics. Based on previous research, it seems to be a good measure for what it is we're actually going after. So the mid-frequency peak is the first peak frequency above any peaks that happen to arise from vocal fold vibration, which are very low in frequency. The mid-frequency, so this peak tends to be between 2,000 to 7,000 hertz, and it strongly reflects the front cavity resonance. So if you think about the articulation of a consonant like sa or sha, of course there's a constriction at some location. The front cavity resonance, if we can get some estimation as to the size of that front cavity, we have some approximation as to the constriction location, and that is apparently what this peak should get at. The other nice thing is that it's relatively unaffected by the laryngeal source, so whether there's vocal fold vibration. In this study, this is automatically estimated, and it's been converted to a perceptual scale of ERB. If you have questions on how we did this, I'd be happy to answer them in the question period, but you can just take my word for it now. Okay, so we'll be looking at the Buckeye corpus of spontaneous speech, which is a pretty well-known speech corpus of American English, and we're going to be focusing on crosstalker variation in the sibilant fricatives, and specifically in their mid-frequency peak. So we have sa, za, sha, ja, 40 native speakers of American English, and the demographics are nicely balanced in this corpus. In total, we have just under 18,000 sibilants and a median of about 470 sibilants per talker to look at. So what we've done is we've derived, as with VOT, we've derived the mid-frequency peak means for each talker and segment, and we'll look at the relationships between each of the fricative categories, so the ones that share an anteriority value and the ones that contrast in anteriority. So starting first with the shared anterior values, uniformity predicts that S and Z, because they have the shared plus anterior feature, they should also have approximately uniform constriction locations. And this should give rise to a strong correlation across talker in the acoustic measurement for constriction location. And that is indeed what we observe. So on the left-hand side, we have S and Z. The marginal histograms reflect the range of talker mean peak frequency variation, reflects the variation in talker mean peak frequencies. And each ellipse here is actually centered on a pair of talker mean peak frequencies, where the size of the ellipse corresponds to a fifth of the standard deviation. And what we can see, and I've got male speakers in blue and female speakers in green, and I've plotted them separately and derived the correlation separately because there does tend to be a slight difference in their overall peak frequency due to physiological reasons as well as social. The correlation is very strong, and also what I want to point out is how close to the line of identity these means are between S and Z. Moving over to sh and zh, which likewise share an anterior value, but this time minus anterior, we have a similar picture with very strong correlation, significant, and the means are very close to the line of identity here. Now, it could just be that everything is correlated, but we are going to turn to the correlations between contrasting anterior values, and we find that some things change. So now we're looking at, we have the voiceless sibilants on the left and the voiced sibilants on the right. These sibilants contrast in anteriority, and at least for the female speakers, the correlation drops dramatically and is no longer significant. And for the male speakers, the correlation does drop a bit for z and sh. I've now said a few times that the phonetic targets should be uniform based on these correlations, so the covariation arises due to underlying identity, but is there a way that we might be able to formalize this a little bit further? So uniformity is a constraint on phonetic realization and not an absolute. How do we go about testing its strength? So one way we've thought about doing this is to model phonetic realization as a Bayesian linear mixed effects regression. We're just using BRMS, which is a nice R package for doing this. And here we've got the R formula for the linear regression, where we would predict mid-frequency peak. So we're predicting variation in mid-frequency peak based on a set of predictors. And these predictors, so the first set are the you can think of them as the distinctive feature values. These should be realized in a certain way that give rise to a set of phonetic targets, and that explains some of the big variation in mid-frequency peak, right? We expect the plus anterior segments to have, say, a higher mid-frequency peak than the minus anterior segments. Similarly, we've got some vowel contextual information that might also affect mid-frequency peak, social information or physiological information like gender, and we also include a random intercept and slopes for the segment features for each talker. So it could be that talkers differ a little bit in the strength of each of these effects on their mid-frequency peak. So we're going to formalize uniformity in the realization of sibilant place as a Bayesian prior distribution on the phonetic realization of a feature within and across talkers. In the case of mid-frequency peak, we expect the place of articulation feature to really call the shots, and the voicing feature should have basically no influence on what the mid-frequency peak, or i.e. constriction location, is. So keeping this in mind, voice should have no influence on the realization of anterior. And so when we look at the mid-frequency peak, there should be no difference in the two targets for the plus voice and minus voice segments. So what we did is we manipulated the prior distribution on voice at the population and talker specific levels. So remember, this is a hierarchical model, so we have voice specified in two locations, one at the population. So in general, voice shouldn't have an influence on mid-frequency peak, and then maybe talkers differ a little bit. But in general, talkers also shouldn't, the effective voice also shouldn't have an influence on mid-frequency peak. So we varied the priors. So the model was always the same. We only varied the priors over the beta coefficient for voice in ERB, and varied the priors over the standard deviation for the bitalker random slope for voice in ERB. And so we used the following priors. You can see that they are all centered on 0 with varying standard deviations. So how much sort of slack are we willing to give the language in terms of the effective voice? So again, uniformity predicts that the influence of voice should be as close to 0 as possible. We compared these models using Bayes factors, and just for convenience, I've converted the ERB standard deviations or ranges here to values in Hertz, and you can see that some of these are very close to 0. The prior distribution is very close to 0, and others, there's a lot of leniency in what the effective voice can be on mid-frequency peak. So in general, we actually do observe a slight and reliable influence of voice on the mid-frequency peak, regardless of which model we use. So it is the case that the mid-frequency peak for voiceless consonants is a bit higher than for voice consonants by about 0.06 ERB, which is, in this model, translates to 1.5 Hertz, but it's a rough approximation because we weren't estimating the model in Hertz, we were estimating it in ERB. For the variation across talkers and the influence of voice, there's actually a similar number. We get a standard deviation of 0.06 ERB across talkers and how much a voice can actually impact the mid-frequency peak. So some talkers really don't have the influence others do. And across models with the different priors, there's actually almost no difference in these estimated influences of voice or the variation across talkers in the effective voice. So it doesn't matter which prior we start with, the data overwhelms it. So now all we're comparing is sort of that initial influence, the starting point for the model, which model is best. So when we look at the fixed effective voice, this is at the population, higher numbers here indicate greater evidence for the more constrained prior. And what we see is that the two tightest priors are actually the winning models. So there's very little difference in the models with prior specifications at these two levels, so 0.01 and 0.1. But after that, then there's moderate to considerable evidence in favor of a phonetic realization process with this type of prior on the population effective voice. Turning to the talker level, so the variation across talkers, we also expect that in general talkers should be the same. They shouldn't have an influence of voice on mid-frequency peak. And here we find that the second model actually does the best. So it's not that there's no variation across talkers. We do get some variation, but it is still constrained to a high degree. So the winning model has a prior with centered on 0 and a standard deviation of 0.1 ERB. So overall, we find evidence for the uniformity constraint on the phonetic realization of sibilant place. And this was observed for American English speakers in spontaneous speech, pretty naturalistic. It's also been tested in laboratory and connected read speech styles with very comparable results. Once again, we can ask the question, is this limited to American English? And how well does this hold across languages? So in the next section, we'll turn to some more cross-linguistic extensions where we might have some answers to this and just wrap up what we've talked about today.